Hello guys, I am Munot and welcome to the School of Physics. So today we are going to do the part 6 of our modern physics series, and today we are going to see radioactivity. I hope you heard this song, Radioactive. Okay, so radioactivity, this is the part 6 of modern physics, Alright, so radioactivity is dependent on very simple formulas, very simple formulas. Like one of them is n is equal to n naught e ki power minus lambda t. Okay, and similarly a is equal to a naught e ki power minus lambda t. Okay, how does this come from? This comes from the formula dn by dt is equal to minus lambda of t. Okay, dn by dt is equal to minus lambda of n. Okay, and these are the very simple formulas. Then there is this time half. Time half is equal to 0.693 by lambda or ln2 by lambda. Then there is this t average you need to know, which is 1 by lambda, or we can say t average is 1 by lambda, or which is also equal to 1.44 times of time of half time. Okay, half life, half time. Okay, then there is another very simple formula which is called so after n half lives, how much will be the n, right? So after one half life it is n naught by 2, then this is n naught by 4, then it will be n naught by 8. So after n half lives, the number of nucleus will become n naught upon 2 ki power n. Okay, so these are the simple formulas that you have to remember in radioactivity. Okay, now I am going to explain in detail what these formulas actually mean. Okay, so listen carefully. Suppose you have n naught nucleus at time t equals to 0. Suppose you have n naught nucleus at time t equals to 0. So what you have to do, that this nucleus will decay. This nuclei will decay and the number of nucleus will keep on decreasing with time. So at any time t, this is the lambda is the disintegration constant for this decay. Lambda will be given, lambda is needed to be find out, whatever. So lambda is the disintegration constant for this disintegration. So at any time t, this is the initial number of nuclei at t equals to 0 is n naught, and this is the nuclei at any time t. So n nuclei at any time t will be given equal to n naught e ki power minus of lambda t. N naught e ki power minus of lambda t. Similarly, activity. Now activity has certain units. Activity is activity. So activity has units called 1 Barraquil. 1 Barraquil equals to 1 disintegration per seconds. Then you must have heard about Rutherford. So 1 Rutherford in terms of activity is having units 10 to the power 6 disintegrations per seconds. Then there is 1 Curie. Marie Curie, as you have discovered, like I heard, she got Nobel Prize for radioactivity. So 1 Curie is equal to it's easier to remember, 3.7. 7 and 3 adds up to 10 into 10 to the power 10 disintegrations per second. So activity also has a similar formula, A is equal to A naught e की power minus lambda t. Okay, now half time has a formula equals to half life. Half life has a formula equals to ln2 by lambda. ln2 by lambda. Now what is half life? Half life is when this becomes n naught by 2. n naught by 2, number of nuclei just halves. So this is half life, and this is equals to ln2 by lambda. And then there is this average life. Average life is time when this n becomes n naught by e. Average life is the time when this becomes n naught by e, and this average life is given by t average, which is equals to 1.44 times of t half. Okay, then after n half lives, this n naught becomes n naught by 2 की power n, because after first half life this will become n naught by 2, after second half life this will become n naught by 4, after third half life this will become n naught by 8, and so on. Okay, so after n half lives this will become n naught by 2 की power n will become n naught by 2 की power n. Okay, so this was about radioactivity. I should also give you a brief idea about what alpha, beta and gamma particles are. Okay, alpha, beta and gamma particles are. So in any nuclear reaction, what we'll do, many times what they do is they combine a mechanics question into a nuclear reaction question. With like, if you have to combine modern physics with mechanics, we can do it very easily using the alpha decay. So what is alpha particles, beta particles and gamma particles? This I am going to tell you. So first of all, I am going to tell you mass. So basically alpha particle is nothing but I am taking some space here. Alpha particle is nothing but a doubly ionized helium ion. It is nothing but a doubly ionized helium ion. So what is the mass? Mass is 4 times of mass of a proton. Okay, 4 times of mass of a proton. And what is the mass and what is the charge? So the charge, number of neutrons to number of protons to charge will be 2 times of protons charge, so 2 positive. And then there is this beta particle. Beta particle is either a positive electron or a negative electron, a positron or right. So what is positive electron? It means, what is the mass? Mass is equal to mass of electron, that is 9.1 into 10 to the power minus 31 kgs, and charge is either positive 1.6 into 10 to the power minus 19 or negative 1.6 into 10 to the power minus 19, depending on whether it is beta positive or beta negative. Then is this gamma particle, which is nothing just photon. So it has mass 0 mass and it has charge 0 charge. Okay, then the velocities of these particles, velocity, so this has somewhere around like approximately 10 to the power 7 meter per second velocity. This has like something 30 to 90% of c, like 3 into 10 to the power 8 per meter per second. And this, as you know, is photon, has velocity equals to c, which is 3 into 10 to the power 8 meter per second. Okay, then penetration power. Penetration, as you know, this can penetrate high. So penetration power, penetration. So this can penetrate less because of lesser speed. Then this penetrates a bit more, and this can penetrate very highly. Then there is this ionization power. Ionization power. Okay, so this has very high ionization. This has very high ionization. Then this has a bit lower, and this has very low ionization. As you know, photons cannot ionize. Okay, cannot. Penetration, as you know, and ionization. Okay, so this was about alpha particles, beta particles and gamma particles. I think this is enough. Okay, I'll give you an example of a nuclear reaction, don't worry. So just for the sake of giving an example, I'm going to show you how to conduct a nuclear reaction with. So what happens is, whenever a nuclear reaction happens, there's some energy released. We'll call that energy Q. So say we are doing an alpha decay. We are going to do an alpha decay. So what will happen in an alpha decay? In an alpha decay, alpha particle will be released. Okay. So say you have this Y. Say you have this X particle, and this X particle has some atomic number mass number A and atomic number Z. Now it converts into Y. So there is an alpha decay happening. It converts into Y. So here comes an alpha particle, which we write as a doubly ionized helium atom, He4 2. So what happens is, in any decay, we have to conserve number of particles, right? Number of particles. So what happens here is that this becomes A minus 4 and this becomes Z minus 2. We have to conserve both the mass number and the atomic number. Okay, so conserve mass number and atomic number. Okay. Now we have done this. Then there is some energy released Q. Which shows that like the mass of the reactant initially was greater than the mass of the products. So there's some kinetic energy. That has gone into Y and helium. So suppose initially this was at rest. So another thing that we conserve is momentum. Another thing that we conserve in nuclear reactions is momentum. So as you know, momentum will be equal then. So my, conserving momentum, my into Vy is equal to m alpha into V alpha. Okay, and we also conserve energy. So whatever energy is released, or whatever is the change in energy, say delta M means mass of products minus mass of reactants into C square, is also equals to the energy that is there, which has gone into the kinetic and the kinetic energy of these particles. Okay, this has gone into the kinetic energy of alpha particle and the new particle Y. This has gone into the kinetic energy of both of these particles. Okay, now on solving both of these, you have to remember this direct result for alpha particle, because it might come, not very sure, but it might come. On solving these equations, we get two simple results. Kinetic energy of alpha particle is equal to my upon my plus m alpha into q. Okay, this is the result number 1. And kinetic energy of this particle Y is m into alpha upon my plus m alpha into q. Okay, so these are the two results that you have to remember directly. Objective questions can come, and he might also twist the question and ask that what is the velocity of alpha particle. So half m alpha v alpha square will be equal to, what is my? As you remember from the equation, we'll write the equation again. One second, I'll write the equation again. The equation said something like x a z converting to y a minus 4 z minus 2 plus he 4 2 plus q, right? So my is a minus y, right? Sorry, m alpha is 4, because so this is half into 4 is 2 v alpha square is equal to my, as you can see, is a minus y is a minus 4 upon my plus alpha is equal to a. Okay, so v alpha square will be equal to a minus 4 upon 2a. So v alpha will become under root of a minus 4 upon 2a, as simple as that. And suppose we have to say find what is the kinetic energy y. So m alpha is approximately 4, m alpha is 4, and this is my plus m alpha is a. So this is 4q by a will be the kinetic energy for this particle y, right? 4 upon a minus 4 plus 4, so that will be 4q into a. So guys, I hope you enjoyed this modern physics series. So you have to do nothing, you have to read nothing outside from this. I guarantee that if you remember, if you just revise all these formulas, there is nothing that you won't be able to do in your paper in the modern physics section. And I started with modern physics in the 12th class because modern physics is the most scoring and has a very high weightage in your exams. So please subscribe to my channel and keep following, keep watching these videos and keep preparing well. Thank you.